Let's talk about ideal gas. Now, ideal gas is a theoretical construct. There's nothing like an ideal gas. But an ideal gas, as thermodynamics was developed, this was some of the earliest ideas. So, ideal gas is defined like this: if a gas is confined in a volume V such that it exerts a pressure P on this volume, we know that pressure should remain same throughout the boundary, because if it's not same throughout the boundary, the gas will flow such that it will equalize the pressure. So this is a sort of an isolated system. This whole system is kept at temperature T. The amount of gas inside, let's say, is n moles. We'll talk about what is mole. An ideal gas will follow this particular formula, that pressure times V should be equal to N times R times T. This is ideal gas. Okay. So, we know pressure. Pressure we know is measured in Pascal, is defined as force over area. We know the volume. N is called the number of moles. R is actually the gas constant. Okay, this is S, constant. It has a value which is given as 8.315 joules per mole per Kelvin. Okay, so an ideal gas will follow this equation, and as you can clearly see that if you keep the temperature T constant, and if you increase the volume from, let's say, T, let's talk about some cases. If you keep T constant, and if you increase volume, actually let's say increase pressure from P1 to P2, then we know that P1 V1 will be equal to P2 V2. Sorry, P2 V2. So from here you can actually deduce what will be the new volume given the initial and the final pressure as well as the initial volume. Also, you can have cases like, say, you keep the volume constant. In that case, we know that P1 V, or actually we can say P1 over P2 will be equals T1 over T2. Again, the same thing, that if you keep the volume constant, I am just playing with the equation, so there's nothing great about it. And these are actually various laws. I don't remember, Boyle's law and Charles' law, something like that. They've sort of combined together and are written as PV equals nRT. Talking about N is called the number of moles. A mole, so 1 mole of a gas or anything actually equals, if you have 1 Avogadro number of atoms, which means, let's say, if you have 1 mole of helium, which means 1 Avogadro number of helium atoms. And 1 Avogadro number, I think, is like 6.023 multiplied by 10 power 23. So if you have this number of helium atoms, that is 1 mole. So let's say if you have a case, you have some volume V, and it is filled with helium, and the number of atoms inside this volume, let's say, is 1.0623. Is it? I think I'm a little confused about this number, but you can always check this. I think it's 6.023 multiplied by 10 power 23. Is just a matter of checking. So let's remove this. 6.023 multiplied by 10 power 23. Let's say this is the number of helium atoms inside this volume V, which is kept at temperature T and pressure P. Then we know the state of the system can be written as PV equals RT, because we know this is nothing but 1 mole. Now, how do you really know that this is the number of atoms inside this? Well, there's no sure way of knowing that, but you can actually you can sort of approximate. We know you will actually, this is what experimentalists have found, and they have found that 1 molar mass is a measure of Avogadro number. So I think it's 2 grams for helium. So for 2 grams of helium, we'll have something like this number of Avogadro number. I'm sorry. So 2 grams of helium will have this number of atoms inside, and I think it varies with different gases depending how heavy or how light they